Assalamualaikum warahmatullahi wabarakatuh. Today our group will present about second order circuit RLC and sinusoidal steady state analysis. For our group members, firstly is me, Sheikh Akmal Hakim bin Syaraha, CE 240220, and second, Sayuga Shamraj, anak lelaki Selvam, CE 250092, and third, Yuva Duke Raj, anak lelaki Parameswaran, CE 250111. The objective the objective of this project are first to analyze the transient response of second order RLC circuits, and second to determine voltage and current response using analytical method. To apply nodal analysis in sinusoidal steady-state AC circuits, and to verify analytical result using circuit simulation software, and improve technical reporting and presentation skill. This is the first question of our project. It is already given circuit with 40 volt power supply, 10 ohm resistor, and inductor with the value of 0.5 Henry, and resistor with capacitor. For the resistor and capacitor value, the question doesn't give the value, so we need to find. So the first step, t less than 0, we short circuit the inductor and open circuit the capacitor. Then we find the I node. We use the Ohm's law, 40 volt divided by 10 ohms, so we can get 4 ampere. For V node equal to 0 because when it's open circuit there is no voltage. To find capacitor, we use the formula omega node equal 1 over square root LC. So the value we choose for omega node is 400. So we just calculate and we get the capacitor with the value of 12.5 microfarad. The next step, t more than 0. So first, alpha less than omega is under damped. So to find a resistor, 150 equal R over 2L. So for under damped, R equal to 150. For critically damped, R is 400, and for overdamped is R is 800. This is the circuit design of our group. For overdamped, we use the Proteus software, and the resistor and capacitor for overdamped is 802.5 microfarad. And this is the circuit of critically damped with a resistor with the value of 400 and with the same value of capacitor to 12.5 microfarad. And lastly, this is the circuit design for underdamped with the value resistor 150 and 12.5 microfarad capacitor.
Hi, madam. My name is Saiga Samraj, and we are gonna continue this presentation with simulation of overdamp. Firstly, we seeing the equation, and for first thing first, will determine the value of resistor alpha and omega. After that, we implant that value in the formula, that is negative alpha plus minus punca causa alpha 2 power of 2, and negative omega power of 2. After we are implementing the formula, we are getting S1 is equals to negative 100 and 0.18 and S2 negative 1492.82. After we are getting the both of value, we are implying it into the IT, that is a times exponent s1t and plus a2 exponent s2t. After we implying the IT, we are getting I1 equals to 4.31 and I2 equals to 0.31. After we are getting both of value, we are implying the VT. VT, the formula of VT is uh, the same. The exponent at a1 exponent s1t and plus a2 exponent s2t. After we combine that a1 and a2, we are getting vt is equals to 231.39 exponent negative 1492.82 t and negative 230.92 exponent power of negative 107 and 15 t. After that, we are continuing with the simulation. If you look at the simulation, we take the calculation as a base model for our coding. Firstly, you can see the circuit parameter, and we are see the timer of factor and the formula of overdamp and certificate solution and voltage response, and finally we are plotting the graph based on our calculation. So now let's look at critical dam and simulation. Firstly, we are determining the value of R, alpha and omega. R is equals to 400 and alpha equals to 400 and lastly omega equals to 400. And we are taking the value and implanting to the formula, that is negative alpha plus minus in square root alpha power of 2 negative omega power of 2, and we are getting a s1 and s2 both same value, that is negative 400. And after that, we are taking the value and implanting to the it, that is exponent power of negative 80 in bracket a1 plus a2 and t, and we are getting a1 value 4a and a2 value 1.6k. After we getting the both value a1 and a2, we are implanting in the vt, that is neg equals to l times di over dt. The last value of the vt is negative 200t exponent negative power of negative 400t in bracket 1.6k. So that proven the formula is working. Now let's look at the MATLAB simulation. As we take the formula and equation as a reference and implanting to the coding. As you can see, we are taking the circuit parameter calculation and given context from the source, that is our equation and answers, and we are taking the time vector, that is the graph of times, the graph uh, taking time of the content, and we are putting the critical dam formula and answers. After lastly, we are plotting the graph based on our answer, and we are getting the graph as uh, top and going down. Now let's look at the underdamp and simulation. As before, we are determining the R and alpha value, but can get the omega value. So we're gonna find the omega value. For R is equals to 150 and alpha is equals to 150. We are implementing the same formula as before, that is negative alpha plus minus square root of alpha power of 2 negative omega power of 2, and s1 we are getting negative 150 plus j 370.81 and s2 negative 50 plus negative j 370.81. After we are getting the both value, we are going to put in the it, that is exponent negative 40 in bracket a1 cos wt and plus a2 sin omega wt. As you can see, we can't find the omega value, so we're gonna put the formula of omega and find the omega. For the formula of omega, that is power root omega power of 2 negative alpha power of 2. Final omega value is 370.81. I mean 3708.1. After we getting the omega value, we are implanting to the Vt, that is L d1 over dt. The final value of Vt is equals to negative 75 exponent power of negative 150 in bracket negative 40 sin 370.81 plus 1.62 power of 0 and 378.81 t v. So let's conclude our formula it's working. So now let's look at the MATLAB simulation. So as you can see, we have taken the formula and equation as a base model for this coding. The same as before, circuit parameter calculation, and we are moving on the given context from the value and answers, and we are taking the time vector for the graph, and we are taking the underdamp, that's its answer of equation and answers, and finally we are plotting the graph based on the answer. And as you can see, the graph is firstly at up and going down at bottom and stay the same level and going the slope. So now let's look at the simulation video. For this simulation video, we are combined three part of the questions, that is overdam, underdam, and critical gam, and combine and compile in one coding, and so that we can easily see the graph and value where it's starting and ending, and determine which is the highest and lowest point. So now let's look at the simulation video. For this simulation video, we are combined three part of the questions, that is overdam, underdam, and critical gam, and combine and compile in one coding, and so that we can easily see the graph and value where it's starting and ending, and determine which is the high.
Hello everyone. This is the question two, where I'm gonna explain about circuit actually. Okay, which is the operating of this is a sinusoidal steady state. Okay, so from your web we can see that the resistor is 2 ohms. We do have two capacitors and two inductors and one voltage source and 1 ohm resistor which is on the current IO lah. So given that the IO is 20 sins 33.3 times and radius per second and minus 45 degrees. So what we can say that for the first inductance, we put 0.3 uh, ampere. Yeah, for the first inductance, we put the reading is 0.3 Henry, and for the second inductance L2 we put 0.6 Henry, and for the first capacitor C1 we put for 0.01 Farad, and C2 we put 0.02 Farad. So from here we can see that we did the simulations for these circuits, and we also did our own calculation for these circuits, and we did comparison for both of the calculation and the MATLAB, that the coding that we did, and we can see the waveform and all that method is state one by one. So for the next slide, we will show us the calculation that we did and the simulations that uh, we did in the MATLAB. Hello everyone. So today right now I'm gonna explain about the calculations then we made, which is on our handwritten lah. So okay, it's this handwritten calculation solved for the source voltage. Okay, so for the source voltage, like what we can say that is Vs by working backward from the no output current. Okay, which is IO. So this is a classic method of an is a AC circuit analysis called nodal analysis combined with a supernode approach. So here's the step one by one. I will explain how we solve it. Okay. So firstly is about the setup and impedance calculation, which is on left columns. So we can say that what we did was we converting the time domain components into the frequency domains. So we got, because since we got a time domain, so we convert it to frequency domains in phases. So from the current, the input of the sine wave is 20 sine 33.33 time minus negative 45 degrees. So we converted the constant reference sines to a cos of delta minus 90 Celsius. So we will be, once we did that, the phase shift will be, the IO will be 20 per negative 135 Celsius amps. So from here, we can say that the impedance, what we calculate on the impedance, the calculated of the complex impedance of the induction and the capacitors uh, using which is 33.33 radius per second. Okay, so um, from here we can see that the inductance, which is so we have to inductance and capacitors formula, and we have stated write it on the paper, which is the ZL, the ZC, where that's how we find the inductance and the capacitors value. Okay, so for the inductance for the ZL, and we found out that after we calculate, we got 20 ohms I, which is J 20 ohms, and for the ZL2 we got J 10 ohms. Okay, so for the capacitor we use ZC formula. So ZL is for inductance and ZC is for capacitor. So what we can say that we found out that the ZC1 is negative J2 ohms, and for the ZC2, which is negative J 1.2 ohms. So the value of the mass line, which is inductance 0.6 and capacitor 0.015, etc., seems slightly tweaking compared to the parameter box likely in a specifically group data requirements. So we move to the second step, which is the solving for the node V2. So since the output of the current known and stood known, and the current since the output of the current we known, and the students, which is we calculate the voltage of the right side node, which is V2 first. So from here the logic, the current of the IO flow through the rightmost, okay, which is through the down, and which is it's a rightmost branch, which contains a resistor of 1 ohm and the capacitor C2 in series. So it shows that the equation for that will be V2 equals to IO times R2 plus ZC2. Okay. So once we calculate they multiply the current facial by total impedance of the branch. Okay, which is 1 minus J 1.2 ohms. So the result will be 2.83 minus J 31.11 volts. Okay. So we move to the step 2, which is solve the node for the V1, because just now we solved for the V2, now we solve for the V1. So what we can see, the V1 we use the super node. So this is the most complex part, where this is since the voltage of the Vs sides between the node 1 and node 2 is on the middle. So we can see that the voltage source, which is on the middle. So we can say that it's a super node. So the equation will be include with the Kirchhoff current in law, which is KCL. So it will be V1 over 2 plus ZC1 plus V1 over ZL1 plus V2 over ZL2 plus current will be equal to 0. So it shows that the calculation or method that we do is like the sum of the current leaving the left branch plus currents leaving in the left inductance plus current leaving in the right inductance plus current leaving in the right branch equals to 0. So we rearranging. So from here what we can see that once we rearranging, they move the known value of V2 and IO because we found out V2 and IO. So they remove the one and the right side of the V2 terms to the left side to solve the V1. So after we did that, the result is after performing the complex algebra, we found out that the V1 is 0.14 plus J 55.33 watts. So we go to the step 3, which is finding the Vs. So from here we can say that the finally voltage source is simply potential of the difference between the two nodes. So explanation between the voltage source, which is V1 minus V2. So looking at the circuit, we can find out that it's a positive terminal in the V1. So the calculation would be 0.14 plus J 55.33 minus bracket minus 2.83 minus J 3.11 will be 2.97 plus J 86.44 volt. So from here we can see the final result, which is in the right column. We can solve the magnitude, which is we use the Pythagorean theorem, which is V equals to square root x plus 2 x power of 2 and plus y power of 2 to find the peak of the voltage, which is 86.49 volts. So in the angle we can saw that it is 88.03. So the time domain will be right in the sine wave. So the voltage source totally will be 86.46 sine bracket 33.33 time domain plus 88.03 degree volts. So this is how we did the calculations for the question 2. Thank you. Hi everyone, my name is Yuva Dukirachana Kiparmeswaran. My metric number is CE250111. So today I'm going to explain about the simulations, which is for the question 2. Okay, basically from here what we can see that it's a simulation video that we did on MATLAB and it's a circuit behavior and we choose a facial based on approach on the handle the complex AC signal. So explain about about the coding. So when it comes to the coding, for the defining constants, we can say that in line 1 through 10, we define that our frequency, if which is 33.33, and the source current, we also set up the components value. So basically, we able to set up the components value for the inductance and capacitors and all. So second, for the facial domain, we can say that instead of using the differential equation, we convert the system into the frequency domain. Okay, so how we can see that in the line 18 to 20, we can see that we converted the source current into the complex facial. Okay, so for the third one, about the calculations. Okay, we calculate the total impedance by using the Ohm's law, which is V equals to current times Z, which is Z is R. So to find the voltage vector. So when come to the inverse transform, we can see from the line 28 to 29, it is reconstructed the time domain signal. So we could plot in the sine wave. Okay. For the second, the result. Okay, what we can see from the result, which is the uh, pointing of the graph. So from here we can see the graph is sine wave, and it's a smooth and perfect graph. So what I can say that the waveform. So as expected for the linear circuit, the output is a clean sinusoidal wave. Okay, it's smooth. So phase shift. You can see that the wave crosses zero at a specific time. So it's like a representing the phase shift caused by the inductor and the capacitor. So thirdly, the critical compression, the smart explanation. So this is the most important part actually. In it is explain why the graph says 30 volts. Okay, while the okay, so basically it's a huge difference actually. So when we can see that the huge difference first is the capacitance sensitivity. In this specific simulation run, we used a standard capacitor value which is 20 microfarad, okay, on the line 9 of the code. Okay, if you can see from the coding on line 9, you can see from that the reading of the capacitor. So in our hand, the calculation, we use much larger capacitor, which is 20 microfarad. Since the impedance is a ZC, and a capacitor of 1000 times smaller creates an impedance 1000 times larger. This is why the simulation voltage is roughly 1000 times higher than the hard calculations. Okay, so when we come to the topology check. So what is called a topology check? Okay, topology check is like the simulation block models, which is complex the series configurations of test maximum impedance. So whereas the hand calculation accounts of parallel branches, which is split the current and lower of the total voltage. So when we come to the conclusion where we can understand and therefore the simulation confirms that the circuit parameters, especially the capacitor size, are critical. So when corrected for the 20 microfarad capacitor in parallel topology, the values aligns with the 86 volt calculate manually. So thank you. That's all from me. And yeah.
For discussion of this project, the experimental data confirms that the damping ratio, controlled by the resistor value, fundamentally alters the transient behavior of the RLC circuit in question 1. When comparing the three states, the underdamped configuration demonstrates the highest speed in reaching 80% of its final steady-state value due to a low resistance that permits a rapid initial discharge. True, though this result in the undesirable voltage oscillations, in contrast, the critically damped design achieved a swift return to equilibrium without any ringing, while the overdamped circuit was significantly delayed by excessive resistive friction. Regarding the second questions, the application of nodal analysis in the phasor domain allow for the successful determination of the source voltage V. The high degree of the similarity between the calculated sinusoidal expression and the MATLAB simulation waveform validates the accuracy of the theoretical impedance model and KCL application used throughout the analysis. In conclusion, this project successfully demonstrated the analysis of second-order RLC circuits and sinusoidal steady-state AC circuits. Theoretical calculations were verified through simulations, confirming the accuracy of circuit analysis technique taught in BEJ10403. The project enhanced understanding of transient behavior, damping characteristic, and phase domain analysis, which are essential skills for electrical engineering application. This is the proof of our meeting or discussion. That's all from us. Thank you.